So okay, यहाँ पे चेंज नहीं हो रहा ना. स्टॉप शेयर करूँ, यहाँ पे तो हो रहा है, वहाँ पे नहीं हो रहा है ना. ऐसा नहीं हो रहा ना. मैं डेस्कटॉप में स्क्रीन शेयर कर रहा हूँ.
अब इसमें हो रहा है.
Okay. All right. So before introducing you to the solar atmosphere, some of the basic properties of the sun. So the sun, as such, maybe some of you are already aware, it is a huge ball of gas. So it the mass of the sun is about 1.98 into 10 power 30 kilograms, as it is written there. But what is interesting, perhaps, for perspective, is that it constitutes about 99.8% of the mass of the entire solar system. So the distance to Earth from the sun is about 150 million kilometers. Again, to put it in perspective, it is about 8 light minutes, meaning the light will take about 8 minutes to travel from the sun to Earth. So then the radius of the sun is about 700 million kilometers, now 700,000 kilometers. So which is about 100 times the radius of the Earth. So then the age of the sun is about 4.6 billion years. The surface temperature, maybe this parameter, many of you should be familiar, that it is about 5,800 Kelvin. The luminosity of the sun is about 4 into 10 power 26 watt. So the composition is, it's mainly composed of hydrogen and helium. As you will know that in the universe, most stars and other matter is mainly composed of hydrogen, and then the second dominant element is helium. And then we have trace elements, of course, in the sun, which we call metals. All the other heavier elements, which we usually call metals. So they are in the trace proportions in the sun. The rotation period, as you have seen, that varies because of the differential rotation from the equator to the poles, around 25 to 35 days because of the differential rotation. So these are the parameters which you got perhaps some perspective of, but then how do we measure these parameters? So, for example, the mass, we can measure using a Kepler's laws. How many of you have heard of Kepler's laws? Most of you have heard, right? So the Kepler's third law, especially that states t square, the time period of the orbital period is proportional, square of the orbital period is proportional to cube of the radius, right? So using that, the proportionality constant, of course, involves the mass of the sun there. So using that, if you know the distance to the sun and if you know the orbital period, of course, then you can measure the mass. But how will you know the distance to the sun or from Earth sun distance? So that is about 1 AU, which I mentioned previously. That distance, generally, all the stellar distances we measure using the parallax method, where you have a target star, and then you have field stars which should be very far away, very distant away from this star, and then you see from different locations along the orbit of the Earth, you know the distance to the sun, and then based on the horizontal distance, what you see in the image of these, according to the field stars, how far this star is at the two different positions, you can calculate the angles using triangulation, and then you can calculate. But of course, for the sun, when you are seeing the sun, then you don't see the other stars, right? So there are other methods that people have devised during the initial times. So during these times, the Kepler's laws were already there, and then the t square proportional to r cube was also there. And then roughly, even though you don't know the distance to each and every planet, they know the proportionality of the distances based on the orbital period, which you can estimate, right? So that we know for the Mercury. And then interestingly, for to measure the distance to the sun, so they can measure the Mercury transit across the sun. Whenever that opportunity came, that comes very rarely, but whenever that opportunity came, some of them measured this Mercury transit time across the sun from two different positions on the Earth. So when you see the Mercury transit from two different positions, you are seeing it almost at a different angle. So then you will see the transit at different locations or different latitudes. So then that will take different times. The transit takes different time. So by calculating that time, then you can get the latitudinal separation on the sun. You already know the separation on the Earth. Again, using the same philosophy, you can measure the distance to the sun. So this was done very early days, and then that was accurate up to like 3% or so to the modern values, which was really remarkable during those times when no other means were possible. So similarly, the radius of the sun, once you know the distance, when you take the images of the sun, you know the angular scale of the sun. So you know the distance to the sun. Using both those parameters, you can measure the radius of the sun. You also have age of the sun. This is a difficult parameter to measure. This is one of the difficult parameters in terms of age, metallicity, or some of the parameters in terms of modeling stars. So the age usually is measured from the oldest meteorite data, whatever you can get, and from the aging of meteorites. So which is about, as you have seen, 4.6 billion years previously. And then the surface temperature of the sun. This, I guess, most of you know the Wien's displacement law. So from that, you can measure assuming that the radiation emitted by the sun as black body radiation. You will see shortly in the course how good this approximation is for the sun case, at least the radiation coming from the sun. So the surface temperature you can estimate using that. And the luminosity, of course, light is coming from the sun. You can measure the amount of intensity per unit square area per unit time on Earth. But then the Earth atmosphere blocks certain radiation. So usually this is for accuracy. This is measured from spacecrafts outside the Earth atmosphere, and then that gives more accurate results. And then you can get you can calculate from the surface area 4 pi r square, and then you can extrapolate this whatever energy you are getting per unit area per unit time. So you can estimate the luminosity of each star like that. And then the composition, mainly hydrogen, helium, or whatever elements present, that abundances we are going to get from the spectral data, spectroscopic data. you will see, I guess, one or so spectra during the course of this presentation, but mainly you might have done spectroscopy courses, right? So from the spectroscopy leaves unique signatures, the absorption lines or emission lines, those leaves unique signatures of the elements which you are seeing, and their amplitudes will actually give you the abundances. So that's one way of measuring composition. And then you have rotation period of the sun. So rotation period of the sun, you can measure, again, we were discussing about Doppler shifts yesterday. So you can measure, because the sun is rotating from west limb to the east limb like this. And then you can, as you see, the emission, whatever the spectral lines you are seeing, they will be Doppler shifted towards you on the east limb, and then Doppler shifted away from you on the west limb. Then you can estimate based on these Doppler shifts, you can estimate the rotation period. So those are the basic properties. So now we can move on to the solar atmosphere. So sun is a huge ball of gas, like I mentioned, and then you have atmosphere around the sun, just like around the earth, but then earth has a rigid surface. But sun, you will see the surface of the sun. Here you see the image of the sun. You see as if it's like a spherically symmetric, very rigid body kind of picture you get. This is a real image of the sun. So from the surface, you will get to know in the future slides the definition of the surface, or the definition of the photosphere. Here, roughly it means the visible surface of the sun at the visible wavelengths. So from there, the atmosphere of the sun starts. And then the upper boundary of the atmosphere of the sun is a bit ambiguous, in the sense that generally atmosphere of Earth or any other object, we call up to where the gravitationally the atmosphere is bounded, right? After that, you can escape from the atmosphere. Similarly, for the sun, you can, of course, gravitationally, you can estimate up to where the boundary is, but then you also have magnetic fields, which can hold the material onto, which can drag the material back onto. So you have to sort of take into account both the gravitational and the magnetic control of this material, and then define a boundary, after which the magnetic fields no longer can dominate and then take care of the material. So that is actually not fixed for the entire sphere. That varies depending on the local structuring that you will also see again in the coming slides. So that is roughly about 10 to 20 solar radii. So that is the top surface of the solar atmosphere, and the bottom boundary is the photosphere, of course. So the photosphere, as you see, is the visible surface of the sun. I don't know if you have seen some of the news in the recent past about the Parker Solar Probe, if you have heard. So most of the news say the Parker Solar Probe has touched the sun, right? It went very close to the sun, very close to the proximity. Their meaning that the Parker Solar Probe has touched the sun is that it entered to the solar atmosphere, this alpha critical surface. It entered several times and came back. So that surface is, of course, like I said, it's not a fixed circle or fixed sphere. So it varies depending on the local structuring of the sun. But then whenever Parker Solar Probe had the closest approach in the last orbit, so it went close to it went inside this alpha critical surface, which means technically it is in the atmosphere of the sun. So that's why you might have seen in the news that Parker Solar Probe has touched the sun. So that is about the solar atmosphere, the boundaries of the solar atmosphere. The solar atmosphere, of course, has different layers. One of the boundary, like I mentioned, is the photosphere, which is by definition the visible surface of the sun in the visible wavelengths. So for precise definitions, you take like 5,000 angstroms or something, where the peak of the visible wavelength, and then where the opacity is equal to 1. We will get back to what is opacity in terms of the solar and stellar atmospheres. So there, when the opacity equal to 1 at 5,000 angstroms, that's where you call, wherever in the solar atmosphere, that's where you call the surface of the sun, that is the photosphere, for precise definitions. And above the photosphere, you have so-called chromosphere. You can see here, this is an eclipse image of the sun. So the moon is eclipsing the sun. You all know what eclipse is. So, and then you can see these colorful patches that is popping out at the rim of the moon, right? at the rim of this shadow of the moon. So then you can see these colorful patches. Those are chromospheric material. Those are actually real colors emitted by the sun. So that's why the name comes, the chromosphere name comes because this is a colorful thin layer above the photosphere. So it is, of course, you can see that when we are speaking of different layers, like we spoke yesterday about the core, convection zone, radiative zone, core, radiative zone, convection zone, and the surface. So similarly, the layers here, we also define several layers in the atmosphere, but then these are not as rigid. You can already see as here, the it is inhomogeneous, right? The layer is inhomogeneous. So you can see some structure here, but there is nothing here, and then you can see some structure here, some structure here. So it is already, the layer is already structured. If you move to corona, it will be even more structured. So this is about the chromosphere. And then if you move to the corona, like I mentioned, it is much more extended up to several millions of kilometers, up to 10 to 20 solar radii. That is the definition I spoke about. And then you can see the corona, how structured it is. You can see different streamers here. You can see all the plasma is structured into these different magnetic structures. So what you also see is that it is extended to much further radial distances, right? It is extended up to several millions of kilometers, whereas the photosphere is just surface and chromosphere is just a thin layer just above it. So the name corona came from derived from the appearance as a crown here. You can see it's like a crown shape. So this shape, of course, varies. So with the solar cycle, you will learn that in the coming lectures about the solar cycle variation of the corona, how corona varies. So you can see this structure. This is during the solar maximum. If you see during the solar minimum, you will see more of the poloidal structure, what Gopal was talking about yesterday. And then almost all these streamers will be restricted to the equatorial belt here. So that will be during the solar minimum. So, and just like you have seen in yesterday, in the between the radiative zone and convection zone, you have a thin layer, the tachocline. Similarly, you have here between chromosphere and corona, we have a thin layer, which is called transition region. That is the transition between chromosphere and corona. Why is there necessity for to define this as a separate layer? That you will see in the coming plots. So this is the an additional layer, transition region. So solar atmosphere, by definition, like you have these four different layers, like I mentioned, photosphere, chromosphere, corona, and then in between the corona and chromosphere, you have the transition region. But like I mentioned also, these are not rigid layers. Just like you cannot define like a fixed radial distance and then you say this radial distance, this should be my chromosphere, or this radial distance should be my transition region. You cannot define because of the local structures you see on the sun. But these were initial times, these were helpful to have a global definitions. So to study global parameters, which we will also be studying in the coming slides. So that's roughly broadly about the solar atmosphere, different layers of the solar atmosphere. But then there are several things you should know before we move into the details of the solar atmosphere. So one of the things, like I mentioned before, is the optical depth, the opacity or optical depth I was mentioning. So optical depth is a measure of how much the radiation is absorbed, right? When from the interior the solar radiation is coming, how much of it will be absorbed at each height, that will be measured in terms of optical depth. So of course, if you want to intuitively think on what factors that will be dependent on, so how much the radiation will be absorbed, on what factors that can be dependent on, can you give me some factors? Can you guess? Initial intensity, of course. If the initial intensity is more, which means per unit area the energy is more, then maybe certainly the more energy can be absorbed. But for more energy to be absorbed in the layer above, whichever is absorbing, there should be enough material too. So it should be dependent on the density of that material. And what else? Yes, the distance traveled by the light, the density of the material, the distance traveled by the light, you can see here. And also another parameter you have that is called K lambda, which is the absorption coefficient. So this absorption coefficient, of course, depends on the composition of the material itself, because the composition will determine how much of my incident light will be absorbed, right? So my incident light can be at certain wavelength, but whether that will be absorbed by my neutral hydrogen, for example, or neutral helium, or whatever is the composition of my material at this particular layer, that whether that will take that radiation or not depends on what level. Maybe if my hydrogen is at excited state or different state where ionized state, then how much the radiation will be absorbed, at what wavelengths the radiation will be absorbed will depend. So that this K lambda is a factor that depends on this composition. So as you can see, the absorption coefficient is dependent on the composition and the nature of the medium. So now, considering variations in this along path, you can see that this I lambda S is the source I lambda, and then this is the initial value. This is at the region where you want to measure, and this is the initial value, minus this K lambda I lambda into rho S. That intuitively speaking, you can understand why. So the actual radiative transfer involves more complicated equations, more boundaries, and several other things that briefly, I think Gopal talked about yesterday, the radiative transfer. But the actual radiative transfer in the solar atmosphere needs a very detailed treatment that itself is a full course. Rather than a single lecture. So what we are putting here is just in simple terms, intuitively thinking what happens if you have this absorption coefficient, density, and then the path length, whatever the path length. If the path length is more, then it will absorb more. So if you take this, then you can, of course, it is simple to arrive at this di lambda by dis equal to I lambda naught into K lambda rho, right? This is quite a simple derivation. You just move this, and then you get di lambda by ds. So if you solve this equation, then we get this I lambda s equal to I lambda into e power minus tau lambda, where tau lambda is K lambda rho s. So essentially, this means intensity falls over exponentially, right? With as along with the path, intensity falls over exponentially, and the exponential factor depends on several things. One of them is the absorption coefficient, another is the density, and also the path length, right? So different factors it is dependent on. So now, I mean, we know theoretically speaking how this intensity should vary. So now it also means if you define this, this tau lambda is, by the way, is optical depth or opacity, what we talk about of that particular layer at that particular height. The fact that there is a subscript lambda means it also depends on the wavelength, right? It should depend on the wavelength because, like I mentioned, the composition, whether it absorbs a particular wavelength or not, depends on the emitted wavelength as well. So that's why I have a subscript lambda there, tau lambda. So if you recall, then I mentioned that the definition of photosphere is also you have to define a wavelength at which tau lambda equal to 1. So that is photosphere. That wavelength is 5000 angstroms roughly. That's what people consider. So now if you take this tau lambda, if there is a layer where the density and thickness of the layer is such that this tau lambda equal to 1, which means essentially whatever the incident radiation that is being absorbed, about 60% of it is being absorbed, right? Rest is being transmitted, about 60% of is being absorbed at that particular path length, right? But at the solar surface, this A lambda can be theoretically calculated by taking into account the composition, whatever the composition we have, this value can be theoretically computed. This cannot be observed, of course, but taking into account the composition, you can theoretically calculate, you know, the density, and you can get the value of K lambda from theory. And then this value, apparently, the solar surface is about 10 power minus 6 per centimeter. So if you take that into account, so this means if you take a path length of 100 kilometers below the surface, then you will get this I lambda will be diminished by about 1 by e power 10 times. So it will be diminished by about 1 by e power 10 times, which means it will be diminished by about 1 by 22,000 times. Whatever incident radiation is there, out of that 22,000 times of that radiation will be absorbed. So then what will be left? Very, very minute fraction of it will be left, that you can understand, right? So this means if you consider the photosphere within a 100-kilometer thick layer, just above the photosphere, 100-kilometer thick layer, almost all the radiation below is never reaching the above that 100-kilometer layer. That is at the photosphere. That is at the surface of the sun I'm talking about. So if you go 100-kilometer below, you will never see the photons coming from there because they are completely being absorbed. That's what this calculation means. Now, so most of the radiation at visible wavelengths, they come from just the surface, that 100-kilometer thick layer. So this justifies the name, that photosphere, the surface where the visible surface of the sun, right? So this is about optical depth. If you have any questions, you can interrupt me in between, and then we can discuss. Okay? Yeah. Yes, photons are getting scattered, but whether that travels in a single direction, same direction, that depends, right? When the incident radiation is coming and incident on certain column, then all you're seeing is how much radiation is passing along this line of sight, right? And then that photons will be absorbed and then they will be scattered around. But then whether they will be scattered in the same direction, that matters. There can also be other processes. For example, even though you have done photon excitation, right? So when the photon are incident on these atoms or molecules, then you have a photon excitation, but they can get de-excited collisionally, right? Then you are losing some energy. So there are other scattering does not mean there is no loss of energy. So there can be loss of energy, but if you take the overall energy into account, of course, it should be conserved. So that is about optical depth. Another parameter that you should be aware of is about scale height. So the scale height essentially comes from the gravitational force of the sun. Any star, any gaseous ball you pick that is glowing in the universe, that is essentially bound by the gravitation, right? So it initially starts everything, the combustion or the nuclear reactions, everything starts from initial collapse, gravitational collapse, right? So we know that the sun is a huge ball of gas. It has a huge mass, which means it has huge gravitational force as well. So it has huge gravitational force, which means it is pulling the material down, because of which, just like in the Earth atmosphere, as we go higher in the atmosphere, the density of the gas comes down. This is because of the stratification. So this is because of the gravitational force. So this density decrease is called stratification. Stratification in the sense you have higher density layer, lower density layer, or gradually decreasing density layers, that is stratification. So this is called gravitational stratification. So similarly on the sun as well, you have this gravitational stratification. So we can estimate the forces. All the forces here are one is the gravitational force. The other is as the material is being pulled down, there will be gas pressure pushing it up, right? So there are only two forces here. One is the pressure force, which is pushing it up, and the gravitational force, which is pulling it down, pulling the material down. So if you take the pressure gradient, which is equivalent to the force of this matter falling force, that rho into g. So this is a simple equation, dp by dh equal to minus rho g. Minus because they are opposite, they're acting in opposite direction, right? So now using ideal gas law, you can replace P equal to, you have rho kBT by mu mh. This is just a simple ideal gas expression in one of the forms. So if you insert that, then you will get rho h equal to rho naught into exponential of minus h by h rho. This h rho is defined as kBT by mu mhg. So this h rho term is called the scale height. So this, like you have seen previously, like intensity here, you can see that the density is essentially, this means density if the mass is gravitationally bound, so then it is the density will be exponentially falling. So theoretically speaking, density should be exponentially falling as you move away from the sun surface, right? So so the density, this h rho, you can calculate provided you have the all you need here is the mass of the hydrogen. This mu, it is dependent on the composition. The gravitational force g is fixed. So the Boltzmann constant. As soon as you know the temperature, you can calculate this. What is this density scale height? So similar derivation can be, of course, if you replace instead of rho, if you get to pressure there, then you can also get a similar equation for similar dependence for pressure as well, the exponential dependence. So the mu actually represents, you have here you have this mh as mass of hydrogen, right? So this mu is the mean mass per particle. So that takes into account like you have different composition, you have hydrogen has different mass, helium has different mass, if you have other elements, you have different mass, that they calculate the mean of those mass. So that value, so considering that once you calculate the mean of the mass, you multiply that by the mass of the hydrogen, then you sort of get the whole mass. That is the idea. This G is not 9.8 because it's not Earth. So that is of course the sun. So if you put the values for the density scale height, considering the surface temperature, which we have just discussed, that the surface temperature of the sun is about 5,800 Kelvin. And then G, the gravitational constant on the gravitational acceleration on the sun is about 274 meters per second square. So that if you take into account, and the mean molecular weight mu, that will come out to be 1.25 if you consider this composition of hydrogen and helium. So that if you consider, then the density scale height will come out to be 145 kilometers. So what it means is that the density falls over, again applying the same logic, density falls over exponentially. Within 145 kilometer distance above the surface, about 60% of the density is reduced from the surface, right? So that's what it means. So this is exactly the reason why you see, when you see the image, you see a sharp boundary, right? Because of this this region, if you move from here to outside, you have a sharp boundary, even though this is a gaseous ball. So you see this sharp boundary because of this gravitational scale height. Another aspect that you should be aware of is so-called limb darkening effect. So if you see the sun, when you observe the sun in a two-dimensional image like this here, I don't know if you are able to perceive the intensity at the center is more compared to the intensity at the edges. As you slowly move towards the edges, it gets dimmer and dimmer. You go in any direction, it gets slowly dimmer and dimmer. So from the center. So that if you're not able to perceive, you can see here I'm plotting the intensity across this line here. You can see that the intensity at the center is higher, and as you move on either direction, intensity tapers off. It slowly falls off, right? Gradually decreases. So this is called limb darkening. So you will see as you move, by the way, this is the solar disk, and then this rim is called the limb. So as you move towards the limb of the sun, the intensity is slowly tapering off, gradually decreasing. This effect is also dependent on wavelength, but another effect, what you can see is if you see in a specific filter, for example, a red filter here. So if you see in a specific filter, you can also see from the center to here, not only the intensity falls off, the color also changes, right? It also becomes more and more redder. So which means here, if you see for different wavelengths, for example, how much it tapers off also depends on different wavelengths. So if you move from calcium K to visual bands to infrared, so calcium K is about 3930 angstroms, and then you move to visual range, so maybe the red wavelength 6000, 7000 angstroms, and you move to infrared, this tapering off has been reducing. So this effect, this limb darkening effect, is also dependent on wavelength. So if you see in infrared wavelengths, that effect is less, which means you will not see as much dimming as you are seeing in the visible wavelengths, or for example, the UV wavelengths. So the reason for this, the physical reason for this, is that as you move towards the limb, you are seeing progressively higher heights. The reason for this is again the opacity, what we spoke about, the optical depth, what we spoke about. If you are seeing from this location, if you are seeing here, because of the opacity, you can reach a certain optical depth, right? Certain optical depth you can reach. But if you are seeing at an angle, this optical depth, this column of material is going to increase when you are seeing at an angle. especially at the limb. So that column of material is going to increase, but then because of the opacity, you are not going to reach as deep as you are reaching at the center of the limb, at the center of the disc. So because you are not going to reach as deep, and then there is another effect which I will be speaking about, that the temperature as you move outward decreases in the sun. Because the temperature decreases, you are seeing at higher layer, the intensity also decreases because of Stefan-Boltzmann law anyway, right? So the temperature you have proportional to the intensity will be proportional to temperature power 4. So there is a strong dependence there. That's why you see this limb darkening effect so strong. This is in fact an important effect because I will get back to that in the coming slides. So you can ignore all the other angles here. The main angle here you can see is this is the local normal. This direction, this is direction is the local normal. This OS is the local normal. And then this angle, this P is the viewer, and then this is the line of sight direction, which means which is the direction the person is viewing it. The angle between the local normal to this, if you consider that as psi, then there is a particular mu defined that as cos psi. So if if you are looking at the center of the disc, which means the viewing angle and the local normal coincides, that means this mu value will become 1, right? So as you move towards the limb, assuming that the local normal at the limb becomes perpendicular to that, right? So if you are viewing that, then that mu value becomes 0. So there is an empirical relation here that intensity as a function of mu, or the cosine of the angle, viewing angle, varies roughly like a lambda plus b lambda into mu. That so this essentially, because ultimately this is because of the angle with respect to the line of sight, right? So that's why they came up with an empirical relation here. But this, as you can see, the subscripts a lambda, b lambda, these are all dependent on the wavelength. That you have also seen in the previous plot, that this how much this tapering or how much darkening, limb darkening happens depends on the wavelength as well. So you need to have these subscripts a lambda and b lambda. So this apparently for in the vicinity of these visible wavelengths 5000 angstrom, these values are about 0.4 and 0.6 for these, which means as you move from the center of the disc towards the limb, about 60% of the intensity will be reduced. Right, so you will see only about 40% of the intensity what you are seeing at the disc center. Only the a lambda parameter will remain, and because mu will become 0, this 0.6 term will go off. Right, so you are seeing only 0.4%, 40% of the intensity what you are seeing at the disc center when you see at the limb. This is at the visible wavelength. But if you go to very long wavelengths, for example, radio wavelengths or so, this b lambda can in fact become negative. So if it becomes negative, that means you are actually seeing even more intensity, right? So you are actually seeing brighter. So that is so-called limb brightening. That also happens when you see at different wavelengths. You have seen this limb darkening tapering off in the previous slides, but then this limb brightening can also happen. So like I mentioned, this effect can be very useful because often to measure, since this is dependent on the plasma temperature, you can use this intensities measurement as a function of optical depth. If you measure the intensities from the center of the limb to the from the center of the disc to the limb, then you are essentially measuring intensity as a function of height, right? So when you are measuring intensity as a function of height, the decrease of intensity is mainly because of temperature. So using that relation, and of course other radiative transfer relations here, you can infer the plasma temperature as a function of height here. So this is a useful task for useful aspect of this limb darkening, from where you can measure the temperature as a function of optical depth. So another important parameter when we talk about the sun is plasma beta. So plasma beta, if you have heard, is the ratio of the gas pressure to magnetic pressure. Okay, so here you can see this will be useful to determine the like I mentioned previously, the layers are not like peeling onion layers or something, just like inside the interior of the sun, they are highly structured and they are inhomogeneous. So that inhomogeneity is dependent on whether the magnetic field is dominant or the gas is dominant at what heights. So that is determined by this parameter called plasma beta. So it is essentially, if you see, it is the ratio of the plasma pressure to the magnetic pressure. I can write here. So it is ratio of the plasma pressure to the magnetic pressure. Plasma pressure to magnetic pressure is given by B square by 8 pi. So magnetic pressure is given by B square by 8 pi and plasma pressure is given by N kBT by B square by 8 pi. So this plasma beta will come out to be 8 pi N kBT by B square. So that is the magnetic, that is the plasma beta. But of course here you see 16 is the value here, and there is another parameter called psi. The reason here is that when you move to the fully ionized media, like in the corona, that I will get back there. So then you have two different, you have both ion pressure and electron pressure as well. So then you have to multiply that by 2. So that's why you have this psi parameter. So rather they define this as 16 pi N kBT by B square, and then this psi parameter is defined as 1 for corona and 0.5 for photosphere. That's the reason. Gas pressure, right? That is both. If you consider 16 for corona, you have both ion pressure and electron pressure. It is a fully ionized medium. So then that N corresponds to ion density and electron density. Total pressure, yes. So that is supposed to be equal under assumptions of ion thermal equilibrium. So then you have both the pressures are supposed to be equal. Yes, so they introduced this parameter psi, so that whether it is fully ionized or partially ionized, not partially ionized or not ionized at all. If you want partial ionized, then you can introduce maybe 0.8 or some, depending on ionization, you can place there maybe. So B square by 8 pi, that I think you will know in the MHD class. You will get to know why B square by 8 pi is the magnetic pressure. So you will get to know, I think tomorrow is the class, right? Yeah. Yes, anyway, the point I wanted to show here is how the plasma beta varies within the solar atmosphere. So this is the height within the solar atmosphere. These dashed lines show different regions in the solar atmosphere. This bottom portion is the photosphere. This in between these dashed lines is the chromosphere, and these two lines is the corona. And this is where the solar wind acceleration region essentially means that from there you're losing, the sun is losing control. That's where I said the critical surface, right? The alpha critical surface is there. From above that, you don't have either gravitational control or magnetic control on the material that escapes. That material just escapes. So that's why that is written as solar wind acceleration region. But anyway, the point here is that this thick line, this solid thick line, yes. So this plasma beta is dependent on the gas pressure and magnetic pressure. So essentially, you have a magnetic field square here, right? You have a B square here. So you were introduced to sunspots yesterday, but I'll be introducing in detail in a while. So you were introduced to sunspots, and I suppose you are familiar that in sunspots are strongest magnetic field regions, and there are other magnetic field regions, right? So if you consider that, then for different magnetic field region, then you should have different beta, right? So that's why in general, this comes from the model, this curve comes from the model, this solid line they plotted for sunspots. And this again, this solid line but thin line, this they plotted this for plages. What are plages? I will discuss in detail, but they are their magnetic field is lower compared to the sunspots. Their magnetic field is of order of few hundred Gauss, whereas sunspot magnetic field is of the order of few kilogauss. So what you can see here is that this on x-axis is you have plasma beta. This particular dash dot line separates plasma beta greater than 1 to less than 1 region. So which means this plasma beta greater than 1 means the gas pressure dominates over the magnetic pressure. Plasma beta less than 1 means magnetic pressure dominates over the gas pressure. This determines this level determines whether the gas is controlling motions over magnetic field or magnetic field is controlling motions over gas. So that's what this particular layer determines. Which means if you are in the photosphere within the sunspot, your plasma beta is still less than 1. Right from the photosphere, your plasma beta is still less than 1. Up until here, up until this alpha critical surface, so your plasma beta is still less than 1 even here. And if you go further beyond, it will reach beta greater than 1 region at certain location. So whereas in the Plage region, if you see in the photosphere, plasma beta is greater than 1, and then slowly it moves to the less than 1 region as you move into the chromosphere and corona. So at even at higher corona, then it again comes back to plasma beta greater than 1 region. So which means again gas is taking over the dominance there. So those are some key parameters I wanted to show. Now we go back to the sun, the spectra from the sun. This is a typical spectra at almost covering the entire wavelength range in the sun, and on y-axis you see the solar irradiance. So the solid line here is the black body radiation curve for 5800 Kelvin, and this zigzag line here, this is the actual observed spectra across these different wavelengths. What you see here is that this agrees very well with this black body radiation curve for most part of it, apart from these deviations because of these zigzag lines. Those zigzag lines or absorption lines or emission lines, whatever present in that part of the spectra, but the overall the continuum matches pretty well with the black body radiation. So this actually the spectra in the visible range, the spectra in the visible range of the sun. So this particular block, which looks like a colorful wall, but this is actually the spectra of the sun plotted plotted from left to right. The wavelength is increasing, and different wavelength bands are plotted one after the other. You are moving from essentially while you are moving, wavelength is increasing like this. Wavelength is increasing in this fashion until you reach here. So you are moving from a blue color to green to yellow to orange to red, right? Slowly you are moving towards bluer colors to redder colors, longer wavelengths, shorter wavelengths to longer wavelengths. So the same spectra is actually plotted here, but of course it is normalized with respect to the continuum. Here you see from 300 to 400, 400 to 500 nanometers, similarly up to 700 to 800 nanometers, you see the same spectra here. But in these plots, at each band, the spectra is normalized with respect to the continuum level. Otherwise, you cannot show them all in the same scale. That's what you have seen previously, that you have seen a clear peak close to the 5000 angstroms, right? So, and then you see a sharp decay on either side as you move to the other wavelength ranges. So to show that on the same scale, here they are normalized. But what is interesting to see is that these numerous absorption lines here, these numerous lines, these zigzag lines, you can see how crowded they are. These lines, in fact, currently, by going through these lines, these atomic data is regularly being updated. Currently in the solar models, we take into account about 100 million atomic lines, 100 million atomic and molecular lines. Even then it is incomplete, it's not a complete list. There are also issues because there are some overlaps, some different lines overlap, there are blending of different lines and you cannot actually identify which line it is. But then currently we take into account about 100 million atomic and molecular lines. But you can see some of the prominent lines here. So you cannot see the names here, but I can say this is, I can read them loud. This is the H alpha line, which is about 6563 angstroms. You all know what is H alpha. I suppose, right? So you know the Balmer lines, Lyman lines, and then right. So the Balmer series, you have H alpha line here, and then you also have H beta line here. So you have iron lines, calcium lines, and then titanium, and then other lines here. So there are several lines. There was also a sodium line somewhere here, sodium D line. But you can also see here there is a band. There is a different bands here. These bands are called telluric lines, which are terrestrial bands. They are of terrestrial origin because the spectra are taken from ground. Then when the light passes through the Earth atmosphere, then there are elements like water vapor, oxygen, or nitrogen, or whatever. They also absorb some of the emissions and then produce these lines. So these are called telluric lines. Those are of terrestrial origin. But you see some of the prominent lines here. You can see, for example, you will see later that these are two calcium K and calcium H lines. This is 3936 or 3970 angstroms or something. So, but then these two lines are pretty broad. You can see. Similarly, if you go to H alpha, that is also going to be pretty broad. So these lines are pretty broad lines. You will see that later in the plot. Yes. Yes. So if you calculate this for any line, why do you see, for example, this crowded portion, this absorption line, this dip for any line? That depends on the excitation levels, right? That depends on within the if you take atomic or molecular lines, there can be in molecules there can be many lines. Even not just atomic level, you also have other vibrational lines and other lines as well, right? So you have different lines. So because these are molecules, this is oxygen, and then these H2O bands, these are water vapor bands. These are some of the prominent telluric lines. So then when you have molecules, then you have even more closer lines. So that's why you see a band of them, because these vibration levels are sometimes very close by. So it depends on when you have molecules, then you have more options to more combinations of these energy levels. So you have more crowded lines there. So perhaps some parameters of interest here is how the temperature and density vary in the solar atmosphere. These are so-called 1D models. Essentially, it means across the entire solar atmosphere, you take again, you're considering a symmetric layer as radially how the temperature or density, how these parameters are varying. That's what you're computing, but these are some empirical models, because if you go by thermodynamics, you will not get these profiles. If you go follow the laws of physics, you will not get these profiles, because the source of all the heat, the source of heat lies in the center of the sun, right? So as you move away, then the temperature or whatever should decrease gradually. So, but that's not what you get here. So here they use certain observations, certain other observational parameters to produce these empirical plots. But essentially what you see here is that the temperature initially from, this is the photosphere, by the way, this is below the photosphere. So from the photosphere, the temperature, which will be around here 10 power 3, some thousands, few thousands, so which is 5,800. And then it decreases gradually to a certain level. And then from there, it starts increasing. It starts increasing gradually. And then there is a region where it suddenly increases sharply. Within a small height region, it increases sharply, and then you have this flattening at the top. So this essentially determines this photosphere from here to here. This is called temperature minimum region. That is the minimum temperature where you have in the solar atmosphere. So that is so-called temperature minimum region. So from the photosphere, you will reach the temperature minimum region. And from the temperature minimum until this transition happens, until this sudden sharp transition happens, you see this temperature, this gradual increase in temperature, this is called, this is the chromosphere. And then you have the transition region, sudden, now you know why we should have a transition region, because there is a sudden transition within a certain small height range. And after that, the temperature reaches up to 10 power 6 Kelvin, which is up to millions of Kelvin, right? Temperature reaches up to very high temperatures. So one of the density, if you have noticed, the density also falls by about 6 orders of magnitude from here to here. The density scale is on the right side here. So it falls over 6 orders of magnitude from the, this is below, in fact, this is below photosphere. So if you consider from here, so it falls up to 10 power 9 or so. So the density falls over 6 orders of magnitude. So this particular aspect, why this temperature, in fact, it should decrease as you move away from the surface of the sun, or radially as you move away, but then it increases. This doesn't obey thermodynamic laws. So then why does it increase? That has been a puzzle for almost a century now. So still we don't know the answer. This is so-called kernel heating problem. Sometimes it is posed as, because chromosphere is also hotter and much denser, it needs even more energy to keep that balance. So sometimes it is posed as chromospheric heating problem, or you can in general talk it as solar atmospheric heating problem. So that's what I mentioned initially. If you follow the regular laws, so then you will find this exponential decrease or regular decrease. But then the gas actually doesn't follow these laws at after certain distance, because the densities fall. The densities fall very rapidly. So then you have to take empirical means. One of the means they take is, for example, here. So they know this part agrees pretty well, the temperature drops, but then suddenly the temperature increases. Why temperature increases? So you have these, yesterday we spoke about these waves, right? These acoustic waves. So those are continuously perturbing the surface. They are always there. Obviously they propagate into the atmosphere, but when they propagate into the atmosphere, they encounter lower and lower densities, but the total energy flux is conserved. So if you encounter lower and lower densities, the amplitude of the waves has to increase. So if the amplitude of the waves increase at a certain point, this amplitude becomes so high, they form shock patterns, and then they start heating the atmosphere. So then that's where you should start seeing heating at some point in the atmosphere. That's the expectation. So similarly, we know from observations the coronal temperatures are million Kelvin from observations since long. Like I said, kernel heating problem is there almost for a century now. So not century, maybe 8 decades or so, which is pretty close to century. So then we know that the coronal temperatures are of million Kelvin. So you should have this gradual increase. And there is also, after initial increase because of this heating, then this heating is tampered down. This gradual increase is because of the hydrogen starts ionizing. So once the energy goes into hydrogen ionizing, then that doesn't goes to temperature increase much. So that's why you see a gradual increase. So all this physics goes into this, and then you have this empirical, based on observations, this empirical sort of curve. So it's not, again, this is for the entire solar atmosphere, right? So it doesn't belong to a particular region. If I talk about, oh, I'll take the sunspot, and then above the sunspot, how my temperature varies, does it match pretty close to this? Overall, broadly, it may be, but then exact values, quantitatively, it cannot match. Qualitatively, it is okay. So then another important part is that the reason I'm saying this now, you have seen some spectra in the visible wavelengths before, but I'm showing you the UV spectra, UV part of the spectra, how it looks now, because you have now seen the temperature structure, how the temperature varies in the solar atmosphere. The relation to this is that if you see the UV spectra, if you see this is 3000 angstroms and you're moving to shorter and shorter wavelengths, right? You're moving to shorter UV bands. So as you move here, you can see this is the continuum line, of course, but then you see these absorption lines here, and then suddenly at some point you start seeing emission lines, right? So this transition happens. This happens around temperature minimum region. This happens because you have an inversion. So you have temperature decreases, and then suddenly you see temperature increasing from that height. So you start to see emission lines as you move to the shorter wavelengths here. But that's not how, I mean, this also means that you can use different lines to observe different layers of the sun as well, right? That you will be seeing briefly. So this is the plot I'm speaking a moment ago now, so that different layers of the solar atmosphere can be observed by using different wavelengths. So you can see this is the same temperature plot, again this 1D empirical model, but here the height is on y-axis and the temperature is on x-axis here. Okay, and it is also not on log axis, it is on actual values, 10 power 3, 10 power 4, and then actual values. You can see the temperature from the photosphere, you can see the bands, photosphere, chromosphere, temperature, and the corona. You can see the temperature initially decreases, gradually increases, and then there is a sharp transition, and then you have this temperature here. So This profile is roughly the same, whether it happens exactly at this height, that varies between region to region, but qualitatively it is the same. But what additional information you also see here is that these different spectral lines, at what height they form. So at what height they form, of course, depends on the densities and temperatures, right? If you have a ionized calcium, for example, ionized sodium or ionized element, for that has to be there, it needs a certain temperature and certain density parameters. Only then it is going to exist, at least at a dominant proportion. So what you see here is that you see silicon 1 lines, you see carbon 1 line, oxygen 1 line, helium 1 line. You also see the Lyman alpha wing here. You see the helium 1 line, helium 2, 304. But what may be of interest here is that you can see the core of the H alpha line is here, whereas the wing of the H alpha line is here. This is what I was talking about. So the core and wing essentially means when you have an absorption line, the center where maximum absorption happens, that is the core, and the wings are on the sides, right, where the less absorption happens. Those are called wings. So that wing actually forms in the photosphere here, and the core forms at mid chromosphere somewhere. So the entire line, if you observe, that spans over several atmospheric heights, in fact. So similarly, if you see calcium K core forms across this many atmospheric heights, and the wing forms here, and the magnesium K core forms at this atmospheric heights, and magnesium K wing forms at this atmospheric height. So if you are observing this line, then you can scan through that line, and then you can actually observe different atmospheric heights that you're going to see briefly, I guess, in the next slide. Yes. So you see here, so this is one of the spectral lines. This is calcium 2 spectral line, 8542 line. This is an infrared calcium line, but you can see the spectra here. So in the spectra, the images that are shown here correspond to this layer, and this layer. So this is the continuum image. So each of these columns correspond to these 3 lines. So as you move towards the core, you can see higher and higher layers in the sunspot. This is in the quiet sun. This is, of course, the continuum, which is the photosphere. So you can see in the quiet sun how the structure varies and how the sunspot structure varies as you move towards the core of the line, which means as you move towards higher in the atmosphere. You can also see in this movie, I will try to run this again. So as the line scans along these different regions, you can see how the structure varies at the top. Sorry. You can see how the structure varies at the top, and as it moves back to towards the wings of this line, then it goes back to the photospheric structure. So now we talk about the solar photosphere in detail. So of course, I'm not going to include too many details, but I'm going to show you at least different characteristic features in each of these regions, and that may be of interest, at least to get an idea of what happens in each layer. So the photosphere, like we discussed, is the thin layer of this few hundred kilometers. In fact, up to from the surface up to the temperature minimum region, we technically consider that as photosphere. So that is the photosphere, and the temperature there drops from 5780 to about 4500 Kelvin or so. This is, again, don't take the numbers to be precise, because these are from the models, and this is not exact value. This varies from sunspot, or you're going to the quiet region or some other region, so it varies from region to region. But then roughly, the qualitatively speaking, the temperature drops as you move from the photosphere to higher atmospheric layers. So this drop also means you will see that as the temperature drops to up to 4500 Kelvin, you will also see some molecular lines forming over, because the temperature is favorable there. So some of the molecules that form over, like CH, CN, vanadium oxide, titanium oxide, sodium, NaH, MgH, calcium H, etc. So these will not sustain in for example, CH would have been easily destroyed in Earth's atmosphere, but because of the low densities there, it can sustain in the solar atmosphere. These are free radicals, in fact. So, but they exist. These molecules exist. In fact, in mid-90s, there was also a mention, huge, I think, public news, that there is water on the sun. So there was water on the sun because they detected water vapor lines in the sun. the ideal place would be this temperature minimum region, but then even that is not enough. Then you see a stronger field, strong sunspot field. Then within the sunspot umbra, the temperatures are going to go even lower. If you go to the temperature minimum region within the sunspot umbra, then the temperatures are going to go even lower. And those are the ideal places when you encounter a strong magnetic field. And then if you see the temperature minimum region above the sunspot, then those are ideal places for such lines to be formed. And indeed, they observe these water vapor lines there, and then they say there is water on the sun. So the photosphere structure roughly looks like this. You have seen this, I think, multiple times now. You can see this is one of the lines, the continuum green line, so-called, that falls, the wavelength falls in the green band. So if you observe like that, you can see how the color changes. But ignoring this limb darkening, what is seen here, mostly you see this white part, and then you see these dark spots. Those are the sunspots, which you know by now. So these sunspots are observed from like 1600s. So from the Galileo times. So we are observing these sunspots since 400 years or so. We know there are dark spots, but the detailed information we are knowing over time, like I think Gopal gave details yesterday that magnetic field, that sunspot hosts a strong magnetic field, that we came to know only in 1900s, right? So this is a typical picture of a sunspot. You can see this dark part. This is the umbra, and then you see this slightly less dark part, that is the penumbra, and then you see this white region around this. But there are also other structures called pores, so which means these are also called naked sunspots, because they don't have this penumbra around this pore, this strong. So each sunspot, by the way, the umbral field is vertical and very strong, and then penumbral field is slightly weaker and inclined. So here you don't have that slightly weaker and inclined field, but you have this vertical strong field in the pores. So these are pores. And then if you move to the quieter part, what I mentioned, you see this granulation pattern. This granulation pattern, by now you know, is because of convection. So this is a signature of convection at the surface, right? So the surface signature of the convection happening inside the sun. So if you zoom into this, if you see closely, you will also see around this granular lanes, you will see these bright structures around this. These bright structures, in fact, host kilogauss magnetic fields. They have very strong magnetic fields, and these bright structures are called magnetic bright points because they have intense magnetic fields there. So those are all one of the some of the structures you will see in the sun. And then if you see in the Doppler gram, you should see in general, if you slightly move slightly higher up in G band or so, you can see there is some cellular pattern. If you see there are some repeated patterns on this, right? This is a Doppler gram. The red and blue means the plasma moving towards you and away from you. The Doppler shifts what you're seeing here. But then you also see certain patterns here. If you take the size of these patterns, these are much bigger than the granules, and these patterns essentially show you the supergranular size, which means this convection happening at a much larger scale as well. So that scale is called supergranulation. Why this is important, you will see shortly, because at the supergranulation sizes, you will see, if you go slightly higher up, you will see these bright bands again. This is a supergranule. You see the granular pattern here, but then you have a cell here, right? That cell was not obvious in the previous plot because that is showing the full disk Doppler gram. But then if you zoom in and then see a small region, you will see again this bright structure here. These cells are called network, that they are organized into a network across the sun. If you see, the entire surface is filled up with such cells, these bigger cells. These are much bigger than the granules. You can see the granular size here, and then these are much bigger than the granules. These are supergranules. But at the boundary of these cells, you have these bright magnetic field structures called network bright points. So you have in between granules, you have magnetic bright points, but you also have in between across this network, at the boundaries of this network, you have these network bright points. So essentially what happens is the small scale magnetic flux that is being advected from interior because of the convective motion, it is going towards the edges, right? It is being transported, because in the photosphere, if you do not have enough strong enough magnetic field, if you recall from the plasma beta plot, in the photosphere, plasma beta will be greater than 1, which means gas will determine the motion, which means this magnetic field, a small scale magnetic field, can be advected by the gas, and wherever the gas is moving, the magnetic field will move in that direction. So that's why you see that at the boundaries of these granular lanes, you will see this magnetic field patches getting accumulated, and then they build up kilogauss fields there. So similarly, you see at the boundaries of these network patches, you have supergranular cells. These are much slower speeds. Granule speeds are much quicker, but these supergranular are slower speeds, but then they build even higher magnetic field patches across this boundary. So these are much bigger, and then they build even stronger fields. Yes. Yes. So why they're brighter, I'll come in the coming slides, but why they're not suppressing, that depends on the strength of the magnetic field, right? So if you have a very strong field, like I said, then the plasma beta curve I showed you, whether plasma beta greater than 1, less than 1, that determines. So there are in the photosphere, if you see, there are other bright regions. If you see, this is a sunspot region, and this is again pore, or this is part of the active region. Within this active region, you will see this bright around these granular lanes. These bright patches are more frequent than they are in the quiet sun. They are more abundant within the active region, or in the close proximity of sunspots. For now, if I haven't introduced active region, you can think of within the close proximity of sunspots, or you can see these bright granular lanes. In the granular lanes, these bright patches are even more frequent. They're more abundant. That regions are called faculae. So they are again strong magnetic regions. Strong, not as strong as sunspot, but they're still strong enough. Stronger than the quiet sun. So now we come back to sunspots being dark, that question. Now the reason sunspots being dark, the umbra of the sunspot is dark, is that if you look at the center, the magnetic field is so strong that it suppresses the convection. So once it suppresses the convection, the gas density within sunspot is going to be lower. If the gas density is lower, that means the opacities are going to be lower, right? If the opacities are going to be lower, the tau equal to 1 layer, whatever you call the surface, is going to be deeper, right? You're going to see deeper within the sunspot. So the deeper within the sunspot, as you see deeper within the sunspot, that seeing deeper within the sunspot compared to the outside region is called depression, Wilson depression. So you are essentially, the surface, what you are seeing outside the sunspot is slightly higher compared to surface what you are seeing within the sunspot. That depth is called Wilson depression. How much of a depth? You can see pictorially here. This is a sunspot from observation. From the model, they calculated how much Wilson depression within this sunspot will be. Again here in Z kilometers here. So at the center within the umbra, this is the sunspot structure. Within the umbra, you see that up to 700 kilometers depression you have within the center of the umbra there. So this is called Wilson depression. So the gas density will be lower because convection is inhibited, material is not traveling up, so then the gas density will be lower. So the gas density will be lower, opacity will be lower, which means the tau equal to 1 layer will be, the surface will be even lower, because you have to see higher dense parts. You're going in reverse direction, I guess. If the gas density is lower, so that means gas pressure is lower, magnetic pressure is higher, so still magnetic field has control, right? So still magnetic field has control of the region. But what another argument for gas density being lower is that the total pressure balance. If you see outside the sunspot, you have purely gas. Let us say magnetic field is 0, which is not true, but let us say magnetic field is 0 outside the sunspot. Then there, all you have is gas pressure, right? If you have a flux tube or a tube of magnetic field, within that you have both magnetic pressure and gas pressure. Imagine having same gas pressure inside and outside, then that means inside the sunspot, you have both gas pressure and magnetic pressure. So you have higher pressure, then that will push it outward, right? But then that's not possible because magnetic field is stronger. So the other way is you drain the gas, reduce the gas pressure, and you have a pressure balance from inside and outside. So that is another way of thinking. So this is about Wilson depression. And then, so why magnetic bright points or whatever these structures you are seeing, small scale structures, why are they brighter, right? So that's what you're talking about. This is the reason they are brighter, because the reason I spoke about Wilson depression earlier is that I want to show you that if you see, this is the tau equal to 1 layer for this bright point. This is a bright structure. Imagine the bright point essentially is a magnetic structure, which means you have a magnetic flux tube, right? So these lines represent these boundaries of this magnetic flux tube, boundaries of the bright point, let us say. And then this is the tau equal to 1 layer outside, and this is the tau equal to 1 layer inside. So inside you have slightly, this surface is slightly lowered. So once it is slightly lowered, you start seeing deeper. Once you start seeing deeper, you are seeing hotter layers, because from the surface, if you go towards the interior, you are seeing hotter layers, right? So you are seeing hotter layers. This hot wall radiation, so the radiation coming from this wall, when you are seeing at an angle, the radiation coming from this wall is what you see. So that's why they are brighter. Now you can ask the question, should be same for the sunspots, right? It should be same for the sunspots. You are again seeing deeper layers, which means you are seeing hotter layers, except the scale of sunspots is much bigger than the depression itself. So the Wilson depression, whatever depression here it is happening in the kilogauss field, the depression is same, but then the scale of the sunspot is much, much bigger. These are small scale elements. So because these are small scale elements, you can sort of see the wall from the side, whereas for a bigger structure, the depression is same, but even if the hot wall radiation isn't enough to hit the entire patch and make it look brighter. So whereas these structures can look brighter because the size of the element is almost same as the Wilson depression. So you can see them as bright. So same for example, the faculae, what we are talking about, they are the small scale magnetic elements again. In fact, I'll come to Plagius, I suppose. Yes. So we move to solar chromosphere. Yes. Yes.
They were brighter.
Yes.
So they were of larger diameter.
Yes. So when we talk about diameter, so they can be distributed across even much bigger scale, like for example across the sun, but then individually those are small bright points only. Individually, that is the diameter of the flux tube. When you want to see, that is the flux tube diameter, you want to see the individual bright points. You should not see the network. There is a network, they are organized along the boundary of this supergranular cell, but if you consider that, it's not a single entity. They are bound only by this granular, supergranular flow, right? They're not bound by connected by the magnetic field in that sense. Whereas in a sunspot, it is all a single connected patch. So that single patch inhibits the plasma motions from all sides. So that's different in that scale. Yes. Yes. No, pores are much larger than these individual patches as well. So we move to the solar chromosphere. So I have only a few more slides. Don't worry, I'll not take too much of your time. So so we move to the sunspot chromosphere. Again, each layer I'll be introducing what kind of features you can look at when you look at the observations of these particular layers. So the chromosphere is the layer between once you move from the temperature minimum to the transition region, between the transition region. So the temperature rises gradually, and then that is where from the temperature minimum you see this chromosphere structure. So across this layer, the density falls by over 4 orders of magnitude. The temperature increases from about 5,000 to maybe at the bottom of this about 10,000, or at the top of this or below the transition region, it can reach up to tens of thousands. So that's how the temperature within the chromosphere varies. But I have already shown you a number of ionized, and then also this calcium 2K means singly ionized calcium, right? You have ionized species, and also you have neutral species like helium-1 or H-alpha, which is neutral hydrogen. So several lines also form within this band. So I have shown you this image previously to show the chromosphere, right? The reason I have shown you this is because you cannot see the chromosphere directly on the disk when you're looking at the visible wavelengths. The reason is that the photosphere is so dense, it is more intense compared to the chromosphere itself. So when you try to see in the visible wavelength directly the chromosphere, you will not be able to see because you are blinded by the light coming from the photosphere. So that's why you take similarly for the corona. So when the disk is being blocked by this moon, so then you will see the outer rim. That's where you see the chromospheric structure. So this is in dominant H alpha emission. But if you go to these lines, the cores of these lines, I have shown you in the previous plot, the H alpha core and the calcium K core or different spectral lines, they form, the core of those lines form in the chromosphere, right? So in the previous era, we were not able to isolate that core because the bandwidth of the filters were not so narrow. But then when you are able to isolate that core to very narrow bandwidths, then you can actually see the chromosphere directly. So that's what is happening here. This is a H alpha filter only from the core, only taking the intensity from the core at each pixel. So that you can see directly the chromosphere here. The features you see, these lanes, these dark lanes, these are so-called filaments. And then you see these bright features, these are so-called plages. These plages are equivalent to the faculae in the photosphere. These plages are same chromospheric features, which means essentially, again, these are few hundred Gauss fields within the proximity of a active region, the sunspot. Here there is a sunspot actually. So, and then within the proximity of that, you have these bright plage structures, which are chromospheric features of the faculae. This is another image in the chromosphere. You can observe with the different line as well. So if you see in calcium K, for example, so you see again a different structure here. This is again chromosphere, but it looks slightly different. You see the plages here, the sunspots here. So what structure you will see depends on the sensitivity of this line to temperature and density. H alpha, for example, is sensitive to density, and then calcium K is sensitive to temperature. So you will see different structures in these different lines. So you can even use different lines to probe different heights in the chromosphere itself. So in the chromosphere, again, you see this sunspot features. This is the photospheric part of this sunspot. And if you move to the chromosphere, you will see how much extended the structure looks like. This is the chromospheric image and this is the photospheric image. The sunspots, you are again aware, the umbra, penumbra, and the part here. These are plages, which I already described. These are the plage regions, and you have these sunspot regions here. And if you go to the chromosphere, of course, you again have this network and internetwork patches. This network now, if you see, it is more hairy-like structures pop up rather than only bright points you see when you look in the lower atmospheric layers. But if you see in the higher atmospheric layers, you will see these hairy-like structures pop up at each of these bright points. So we will briefly talk about what are those, but you can see for a supergranule, the Earth-2 scale here. So in the chromosphere, another features you will see when you look at the limb is these so-called prominences. So they are bright structures which you saw in the eclipse image as well previously. These bright structures of limb. So again, you can see the Earth-2 scale here. These are the bright suspended. This is essentially the suspended plasma in the suspended cool plasma in the solar atmosphere. So if you go by heights, the geometric heights, if you go by geometric heights, chromosphere should not be existing at these heights. But still you have the chromospheric material being suspended at a larger height. That's why I was saying you should not go by geometric height at every region and say my 2 megameter or 2,500 kilometers should correspond to chromosphere, and then above that should be transition region or corona. We cannot go by that because the structure depends on various other factors. So how the material is suspended, it itself is a big interesting problem. So because this is a cold material being suspended in the atmosphere, so people have come up with different theories that the magnetic field is bent around this material. So wherever that bent, actually the magnetic tension actually supports this heavy material, this dense material from falling down. There are other different models, different interesting models you can look after. So this is another prominence here. If you see these bright structures on disk, like I mentioned a while ago, these appear dark. The reason you look at H alpha, and at H alpha wavelengths you have a bright radiation coming from the photosphere. That radiation is being absorbed by this dense material suspended. So you will see these features as dark. Whereas when you're seeing off limb, then you don't have that background of photosphere off limb. So then all you see is the emission coming from these dense material suspended above the limb. So that's why you see them as bright, whereas when you see on the disk, you see them as dark. But they were initially named when we don't know the physics of it, when we didn't know the physics of these structures. These dark structures were named filaments, and then these bright structures were named prominences. Similarly, you will see in solar physics, there will be so many different technical jargon, all corresponds to like roughly the same features. That is very common in solar physics. Even recently, some of the bright structures that appear in the corona are called campfires. So that became quite popular after launch of a recent satellite. So those campfires are essentially brightenings you see in the sun, but at a smaller scale. So those brightenings have been discovered before at a bigger scale. When you see with a high resolution instrument, you see them at a smaller scale, and then they gave a different name just based on the visibility. So now you see that this particular region, you see this is the continuum region. So, and then you see this iron one, this circular polarization, this shows the magnetic field. This is the linear polarization. I did not talk about the different ways of observing because that will take a long time. You can measure the polarization of the light coming towards you. You can take the spectra, essentially intensities as a function of wavelength. You can also capture images, simply intensity. Depending on what you capture, you get different information. So here, by capturing the circular polarization and linear polarization, they get the inclination of the field and also the strength of the field. But you forget about that. This is continuum. What you can see is that you move to calcium K core, H alpha core, and calcium K core. You see these different structures. These hairy-like different structures, these are called mottles or fibrils. Depending on whether they are in the quiet sun or whether they are in the active region, they were given different names. Whether if they are in the quiet sun, mottles, and if they are in the active region, fibrils. But then if you see the recent literature, they have been interchangeably used, like whether fibrils or mottles, they interchangeably used for all these finger-like structures coming from the network region. So if you see those structures, those dark structures off limb, again they will appear bright. Again, these hairy-like structures off limb, these were named as spicules. So on the disk, this is a movie of this. This is a network cell, and around this network boundary, you see these finger-like structures coming out of this boundary. So these are these are high-speed dynamic events as compared to mottles and fibrils. So these are so-called rapid blue-shifted events and rapid red-shifted events. You don't have to know the technical terms. Essentially, if you look at the spectral line, so what it means is that you will see an enhanced absorption in the blue wing or the red wing. Depending on that, they're called rapid blue-shifted events or red-shifted events. Essentially, it is the material driving coming out from the network region. So those are some jet-like features, like spicule-like features. So if you go to the transition region, it is a thin region, like I mentioned previously. In the transition region, this is an image taken from early 2000s. So this image was not taken from a single instance because this was taken by a spectrometer. So I mentioned different observational techniques I did not talk about because we cannot cover that. But then if you are observing spectra, you have to compromise one of the dimensions on the detector because you want wavelength dependent intensity. Then all you have is intensity across one dimension. So to observe this transition region, actually several rasters were scanned and all of those pieces were mosaic, those stitched together to form this image. So this image, observing this image took several hours. So what you can see is that you see a brighter limb as you move from the center to towards outside, right? So you can see a brighter limb. So is this limb brightening? It appears so, but then it is not. The reason it is not is because the wavelength you are observing is actually optically thin, meaning all the light you are seeing, all the emission that is coming along the line of sight will be integrated. All the emission will be integrated. That is optically thin emission. So if that is so, even when you are looking at the limb, you have a longer column. That means you can still see deeper. But when you have a longer column, then you have longer emission, higher emission because of the longer column depth. So that's why you see this bright rim around this. It's not because of the same limb darkening process. But if you look at the radio wavelengths, I don't have that image, I suppose, but if you look at the radio wavelengths, you will see higher heights and you will see that actually limb brightening happens. So we move to the corona now. Again, the corona, I mentioned that it is the disk is being blocked. Then only you will see the corona in the visible wavelengths, because corona is about 1,000,000 times fainter compared to the photosphere. So you have to block the disk to see the sun if you want to look at the visible wavelengths. But if you move to the extreme ultraviolet or X-ray wavelengths, for example, then you can see the corona directly, because that part of emission coming from the photosphere is less compared to that coming from the sun. So you can see the entire solar disk here. But of course in the extreme ultraviolet wavelengths, and if you move to the X-ray wavelengths, this is how the structure looks like. But what you can see in both these images is that the plasma here is all these bright structures or into these finger-like structures or loop-like structures. All these wherever it is brighter, it means the dense plasma is being present there. So the denser plasma is being organized into these bright structures, and if you look at the corresponding photospheric signatures, you will see stronger magnetic fields at the foot points of those. So essentially these loops are connecting these stronger magnetic field regions from one polarity to the other, and along these loops you have these enhanced density plasma being trapped inside. So you see similar structures here, but what you also see perhaps briefly is these darker patches. These darker patches are called coronal holes. You also see smaller bright point-like structures at occasional places. So these are different. If you look at other images, perhaps in other coronal wavelengths, you will see this dipolar-like structures here coming up, especially in the solar minimum region. Those are so-called polar plumes. So now I have last 3 slides or so. So I have given you an overview of different structures that you see as you move from different layers, right? But then you perhaps also want to know that why actually we study these different structures. So some motivation was given yesterday by Gopal, and you will also have some motivation given in terms of space weather by Shatabdo after my talk. So you have space weather implications. You need to understand what is happening in the sun. Apart from that, we also want to understand physics of the sun, what is happening on the sun, so that we can apply to other stars, or we can apply that can improve physics in general. You have seen when Gopal explained the solar neutrino problem yesterday, essentially it improved the particle physics. The solar physics has improved, the observations of the sun has improved the particle physics by proving that actually neutrino has different flavors. Neutrino has mass, so it can switch between different flavors. So it enhanced the particle physics. Similarly, by exploring different problems on the sun, you can improve, there is a chance to improve physics overall. So one of the things I mentioned already, that the solar corona is about 200 times hotter if you estimate the temperatures, and to keep that at the temperatures, it needs about 10 power 7 erg per centimeter square per second. You need that high amount of energy, but if you don't supply that, it will cool down. So the corona will cool down within a matter of hours to days. Of course, that doesn't happen when you look at the coronal images. That means something is supplying this energy. What is supplying that energy? That has been a mystery. So that is one of the problems. And then another picture, what you see here is the plot here shows the solar wind speed as a function of latitude here. So the solar wind speed, this is close to the equator and this is closer to the poles. So these are spacecraft observations, and you can see the solar wind speed is much higher towards the poles, and it is much lower towards the equator. But the speed values themselves are pretty high, that they are about 600 kilometers to 800 kilometers per second. These values are very high, and they could not be explained by using simple thermal expansion, because you have 1 million Kelvin plasma. So by using simple thermal expansion physics, you cannot explain such high speeds. So there has been some missing energy that is feeding into the solar wind as well. So these are the different problems. So there are other interesting physics as well. I did not include for the sake of time. So there are other interesting physics problems as well, like I mentioned. So all those motivate you to understand what is happening on the sun and try to improve, connect with the physics that you learned. Okay, that's all I have. Thank you. We can have questions. We can continue the discussions as well during break, but we can have questions now. Any questions?
We talked about plages around the sunspot in the chromosphere. Does every sunspot have a plage, or there are specific types of sunspots that have plages around them?
Yes. So the region with plages and this sunspot, this entire region, if you look in the corona, you will see these bright loop structures, and they are also centers of activity. That's why we call them active regions. I did not mention that. Now, so when a sunspot comes, it has a single polarity, and but it cannot come with a single polarity, right? It always comes in pairs. But the trailing polarity, if you see, they are more dispersed. So that dispersed flux will be of lesser strength compared to the leading polarity, which has a stronger strength. So this trailing polarity will always be dispersed in terms of a weaker field, which will be about 300 Gauss or few hundreds of Gauss. That will look like plage. So in that sense, plage will always be there. If you have a sunspot around that active region, plage will always be there.
I also had a question about coronal heating.
Mhm.
Does the coronal temperature has any correlation with the solar cycle that we studied yesterday? Like the changes in the maxima and minima of the number of sunspot, does that affect the coronal temperature in any way?
That's a good question. So the only problem with this is that when you look at the corona, you have these different loop structures, right? It is highly structured, highly inhomogeneous.
Yes,
It's not homogeneous. So depending on the structure you take, temperature can go up to 20 million Kelvin, 10 million Kelvin, 1 million Kelvin, depending on the structure you take. So the corona evolves over much shorter scales compared to the solar cycle. So you don't have a global correlation with respect to the solar cycle, but it evolves much rapidly over shorter time scales. So you will see, for example, 20 million Kelvin within an hour if there is a flare or something happening.
Yes, sir.
So, and then there are also other loops which are 3 million Kelvin, 6 million Kelvin. You will see other temperature loops in the vicinity of the same 1 million Kelvin loops, same active region loops. So in that sense, you have a broader variety of these temperatures within the same instant. Then it is difficult to ascertain like whether you have a correlation with respect to a broader value of solar cycle. Okay.
So what changes is actually the X-ray emission, because that depends on the active regions, how many active regions are, not really the temperature as he pointed it out, but the emission changes during if there is X-ray cycle, probably they can look. Okay, questions?
A streamer belt.
Mhm.
What is this streamer belt?
So those are I'll show you. Yes, these are the streamer structures. So you will see the magnetic field organized into during solar maximum. So you will see the magnetic field being organized into these large loops with these open field regions above this. So if you see the magnetic structure, then you will understand how this plasma is being organized into these streamer-like structures. They are called streamers because they stream plasma around these regions into the solar atmosphere. So around this region, plasma is continuously streamed outward. So that regions are there all along here. But if you see the corresponding magnetic structure, then you will understand that how they could stream, because you have an open field region surrounding.
And during the solar minima, that streamer belt will near the equator.
Yes. So this streamer belt will be mostly confined to the equator, and you have a sort of poloidal field at the poles.
And what are the alpha win critical surface?
Yes. So that's what I spoke about. It is a surface where the magnetic field no longer has control of the plasma. So which means the plasma beta again becomes greater than 1. So let me go to that slide.
That is in the corona.
Yes, it is in the corona, but outer corona. So that's where the definition of corona ends. Like that is within which you have both gravitationally and magnetic control of the sun for the material. But beyond that, the magnetic field doesn't have control. The gravitational field also doesn't have control, which means material can easily escape. So that is
Yeah.
the surface, that critical surface.
That have a fixed value, or that depend upon the minimum maximum active region.
That will vary a lot depending on the structure, minimum, maximum, that will vary a lot.
And what are these alpha wind waves that
Alpha waves. So
Alpha
you
waves.
that will be taught tomorrow.
and there is another that is heliospheric.
That is the definition. Like that alpha critical surface is the surface of outer boundary of the corona. We can say that. Yes. Yes, you can continue.
Okay, yeah, I have one that is heliospheric current sheet.
Mhm.
What is that heliospheric?
So that comes, heliosphere is much broader. So this is just the sun atmosphere, right? Heliosphere includes the planets. And if it includes the planet, the solar wind that is coming out of the sun, that has a pressure balance with the interstellar medium just outside the solar system. So that is where the heliosheath or heliopause, that's where the boundary of the solar system itself is. So there maybe heliospheric current sheets will also be there.
No, means I didn't understand that how these heliospheric current sheet form. Means continuous ejection of plasma.
So you have to know what a current sheet is for
Yes,
that to know.
yes.
So you have to know that current sheet is a boundary where the opposite magnetic fields come nearby, the stressed fields come nearby. So wherever that configuration happens, you can have a current sheet. So heliospheric current sheet, even within the heliosphere, you don't have to go until the heliopause or heliosheath. There certainly can happen. It can happen within the, whenever there are CMEs, or you can have a heliospheric current sheet, right? Within the.
So it comes because of the global magnetic structure of the corona, but I think he showed it yesterday.
Yes.
When you have a like global
The extrapolated
yeah,
magnetic fields.
extrapolated magnetic field, you have a global magnetic field structure. From there, you have different polarities coming towards each other near the equator, and that's where you get the current sheet at a very large distances away from the sun, and that's what he's saying.
Yeah. Yeah.
Current sheet.
Yes, means where North Pole and South Pole of the magnetic field lines are
Yes,
interact,
I think
then-
Shatabda will talk about afterwards. Yeah. Yes.
Very far away. Okay. Good. Any other questions?
Sir, at the end, you talked about a problem, I don't know, maybe some faster wind speeds that are not explainable.
Yes, yes.
So he also talked about some current sheets. I'm not sure, I haven't read about them. But some people would have tried to explain this with magnetic reconnection. I don't know why.
Yes,
could you
because-
explain why that?
Because
will
that
not
is the
work?
boundaries of opposite magnetic field. That's where you current sheet is formed.
Hmm.
That's why there is a possibility of reconnection there.
Hmm.
The thinner the current sheet, the closer the opposite polarity magnetic fields are, and the possibility of reconnection there. Will you be talking about Vaibhav tomorrow or no? Not about this. Shatabda, will you be talking about no? So yes, yes. Yeah. Yes.
Because the kind of pattern during the solar minimum, the speeds near the pole are higher, right? And
So
that is where
when we talk
colloidal
about
foil
current sheet,
forms.
those are about magnetic fields.
Huh.
The pattern here, it's just a representative way of showing how much the solar wind speed is at this place, this place, this place, at these latitudes.
Mhm.
So it is only showing the solar wind speed. This is the axis here that shows the solar wind speed. This is 1000 kilometers per second. This is 500. So the values here are between 500 and 1000. Somewhere around 800 kilometers per second is the values. They are also more regular, like they are more regular. Whereas here towards the equator, they are more irregular, like they vary a lot. And then they are much lower speeds. Towards the equator, they are much lower speeds, less than 500 kilometers per second. These lower speeds, one can explain considering the thermal expansion. If they are much lower, they can thermal expansion because you have the hot corona here. So considering thermal expansion, some wind will be moving faster. So that you can explain. But these 800 kilometers per second speeds, that you cannot explain.
No.
Even considering thermal expansion, you cannot attain such high speeds. So that means there is some other force that is driving these winds to high speeds, right? So that is called the solar wind acceleration problem.
Yeah. So
Hi, sorry, I'm joined late. I'm Dipankar here. Yeah, so the global magnetic field structure also crucially dictates this speed distribution. So here, what is overplotted here is also the, on this image, which is also giving you an impression that the fields are more closed into the equatorial region. So whenever you have a closed magnetic field region, then it is much harder for particle to escape. Whereas in the polar region, the magnetic field is more open. So it's a much easier channel for the particle to accelerate. So what Krishna is pointing it out, of course, we need to have a mechanism for acceleration. So there are waves and other things are invoked for this acceleration. But naturally, you can imagine whenever there is a closed region, it is much harder for material to escape. Whereas the polar regions has open magnetic field, and that becomes a easier channel for the acceleration of the solar wind. So fast wind is mostly seen in the polar region. The slow wind is seen in the equatorial region. Change with the solar cycle, exactly. Yes. So he's showing one. So since you asked question, I will probably show you another image when it is during the solar maxima. During the solar maxima, the field will not be so open in the polar region. So the distribution will completely change. So the global pattern of the slow wind and the fast wind is completely dictated by the global magnetic field structure, which is again a completely solar cycle behavior as well. Probably I will just add, this other discussion was happening about the temperature, whether it is changing from the solar cycle. It does have a change in the solar cycle, because what Krishna was also pointing out, the requirements are different. When you have a maxima, you have more active regions. So the heating in the active regions, our energy fluxes requirement is more. So you have 10 to the power 7 arcs per centimeter required, whereas in the quiet sun, it is 1 order of magnitude less. So Corona is hot overall, but this, at different locations, the requirements are different. So during the solar maxima, you have more active regions, so you have much more requirement in terms of heating those active regions up to the, millions of Kelvin, with the energy flux requirement of 10 to the power 7. So in a way, there is a variation in the heating also. If you look at it, the local, spatial locations.
In that sense, you need more energy,
Right.
but that doesn't mean that will result in more temperatures. The
Yeah,
plasma
temperature requirement is more or less the same.
Same.
But the, since you have more regions to heat up,
Yes, you need
so
more
you need
energy.
more energy.
That
to
can
supply.
vary over the solar cycle. Yeah, that is correct.
Okay, further questions?
Sir, coming to that transition region, we see that there is a very fast variation in rise of temperature. Is that a variation common all over the sun if we trace, or
Yes.
it shows some variability in that rise?
Yes, that variation is qualitatively common. That transition region, by definition, over a short region, you have very large increase in temperature. That happens because of a couple of reasons. One thing is you have radiation energy input coming from the surface, and you also have energy input coming from the corona itself, because corona is 1 million Kelvin, and the temperature, the chromosphere below is about few tens of thousands of Kelvin, which means you will have thermal conduction from corona, and you have constant energy coming down towards. So both these energies will form a thin layer over which you have a sharp increase in temperature. So that's how we have the transition region. So that happens everywhere, because you have chromosphere and you have corona, you always have this conduction flux coming downwards.
And as we see that we see the trend that it goes sudden from absorption to emission spectra all over the.
So that happens around here. You have the temperature inversion. So you have the temperature decreases, and then temperature starts to increasing again, right? So you have whether you have absorption line or emission line depends on what is the background, whether it is a colder gas, hotter gas, right? So then you have this inversion coming up. So that's why you have these absorption lines suddenly changing to emission lines.
But that has no correlation to coronal heating.
No,
Okay.
that has nothing to do with coronal heating.
Thank you, sir.
Okay, any other question?
So when we talked about, someone asked about the corona, and you said beta is smaller than 1 for coronal heating, the coronas. And when we looked at the beta pressure, the graph, we saw that beta is smaller than 1 at the given heights only for sunspots.
Yes.
So are the coronas, the loops only seen above the sunspots? or will we see them in other
Yes.
places too?
So these coronal loops, all magnetic structures are associated with these active regions
Yes, sir.
typically. But still, when I say plasma beta less than 1, there are certain loops that it can happen. Suddenly they can become overdense because of flares or something. You can suddenly become overdense, and plasma beta can occasionally go higher than 1. That is possible as well. But in general, these strong magnetic field regions, you will have plasma beta less than 1. If the field is weaker, like in plages, the whole point of this paper was to show that even in the corona, even in the lower corona, plasma beta can go greater than 1, so that one has to be careful. That is one of the important aspects of this paper.
Okay. Any other question? Okay, if not, then we can go
a
for
break.
tea break, and
already-
we will reconvene at 11:45. So let's have it only for 15 minutes.